and welcome to the mathleague YouTube channel. The following video was recorded by one of our staff members.
Hello, I am doing this team problem in this computer lab. They're asking us to find the number of IP addresses fitting where we're in the computer lab that have at least 1 0. And the thing is, the IP addresses, there's 4 numbers. Each number could be from 0 to 255, and they're separated by 3 periods. And there's going to be a lot of numbers to consider. Hey, good thing this is a team round, so I'm going to go contact Chinmay and Isaac, who work on this problem, and see what we can come up with. Hello, Chinmay and Isaac?
Here we go. So firstly, we have this combinatorics problem. We just want to find the number of IP addresses that contain the digit 0 at least once. And it's going to be a lot easier to just count the number of IP addresses that don't contain the digit 0 and then subtract them off using complementary counting. So how many numbers do not contain the digit 0?
I have an idea. Let's work our way up from 1-digit numbers to 3-digit numbers.
To do that, first let's find how many of the numbers from 0 to 255 contain at least 1 0. So those are 3-digit numbers, right? And so either the second digit could be 0 or the first digit could be 0. So if the second digit is 0, there'd be 26 options, which are basically all the multiples of 10 going from 0 to 250. So that's 26 of them that contain 0 there. And then the other possibility is that there could be a 0 in the second spot. And for that, the first digit could either be a 1 or a 2. And then the last digit could be anything from 1 to 9.
Hold up, why 9? Couldn't the last digit be 0? Wait, that would be overcounting as we covered that earlier. Never mind. Go on, Chinmay.
So that's 2 times 9 or 18 more numbers that contain a 0. So in total, we have 44 of the 256 addresses of the numbers from 0 to 255 contain a 0.
Okay, so 44 digits do contain a 0 from 0 to 255. I think this means 212 numbers don't contain a 0. I think Isaac's also getting that with my original strategy of working the 1-digit numbers up.
212.
Alright, this casework makes sense as we're doing constructive counting for digits, but that 3-digit section looks pretty involved. What happened?
We need to take some number ranges because we can't just list out all of the 3-digit numbers.
Oh, I see. Making sure we stay in bounds. In that case, I think we agreed that 212 numbers do not contain a 0. What's next?
So the total number of addresses is 256 to the power of 4. And then we want to subtract off the ones that don't contain any zeros to find the ones that contain 0 at least once. So out of these 212 numbers, we can choose any of them for each of the 4 integers. So we just subtract 212 to the power of 4. This is what n equals.
So that's the combinatorics part of the problem. Now we know how many IP addresses contain the digit 0 at least once.
But now we need to find the largest prime factor of n. Well, I have a calculator, fortunately, so I can input that out, and this ends up being 227,500,4160. They really want us to factorize that?
So we have a difference of 2 fourth powers, so we can use the difference of squares to factor this as 256 squared plus 212 squared times 256 squared minus 212 squared, which can be factored again using difference of squared as 256 plus 212, and then that times the difference of the two numbers. So this is how we'd factor that into smaller parts, and then we can try to find what the largest prime factor of this expression is.
Now most of those numbers are a lot nicer to look at. There's 2 3-digit numbers that we can factor. These numbers are even, so we can factor our 2's, then work our way up towards larger primes, as I've done before. And hey, looks like we're getting similar factors even though we started differently.
Okay, how about this value over here? Well, we're kind of out of luck with this value. We just need to compute this by hand and then factor it.
This ends up being 6905.
Good thing calculators are allowed on the team round.
And this is divisible by 5, so we divide out the 5.
I can just calculate that out to be 5 times 1381. Now I just need to factorize 1381 unless that's already a prime.
Well, you have as a team test, you should have someone dedicated to finding out whether this number
This ends
is
up being a
prime.
prime. You can check that by checking if it's a multiple of all the primes up to the square root of the number. So the square root of 1381 is just over 37. So you can check the primes up to 37 and see that none of them divide this.
So 1381 is a prime number, and that's going to be our largest prime factor of n.
All right, thanks Isaac and Chinmay. That was quite an involved problem. Chinmay? Hello? Anyone?
All right, I'm back.
Okay, it seems I'm disconnected.
Oh. Well, that says something about how bad our campus Wi-Fi is. I can't believe we're able to solve an entire team problem before the Wi-Fi was able to cut off.
Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.